Hello, friends. Today we're going to be continuing our study of trigonometry and the unit circle, and we're going to be looking at the tangent function. When you learn basic trigonometry, you learn sine, cosine, and tangent. Well, tangent, the way that we look at it here is totally based on sine and cosine. Okay, so again, the unit circle and the sine and cosine values around the unit circle, they are the basis of everything. So we're going to be looking at some other functions like tangent and then some others, but they're all going to be based on the unit circle and the sine and cosine values. So here's the first thing for us to realize about tangent. Tangent is, you've learned it as the opposite over adjacent, right? And so when we have an angle here like this, the opposite side is the y value, right? And the uh, adjacent side is the x value. Now, if you look at that, that's just slope, right? Y over x, that's rise over run. So the tangent of theta is going to be equal to the slope of this line that's being created here. And so that's what they're saying here. Tangent of theta equals m. M is for slope, right? In slope-intercept form, y equals mx plus b, etc. Also, since the y is the sine value and the x is the cosine value, then tangent can also be looked at as sine over cosine. This is really helpful when we're looking at the unit circle because we can take the sine value divided by the cosine value, and that gives us what the tangent value would be. And so let's begin, and we're going to look at quadrant by quadrant. So in the first quadrant, okay, so what would tangent be at when theta equals 0? So when theta equals 0, tangent of theta is going to be, so it's the rise over run, but the rise is 0, right? What's the slope of this line? It's 0. So the tangent of 0 is 0. Got it. It's too thick right now. And then as theta increases, tangent is going to increase, right? So let's imagine that this is something like 30 degrees, right? So tangent of 30 would be sine over cosine. So the sine is 1/2, and then cosine is root 3 over 2. So this ends up being root 3 over 3. The twos cancel out. We don't want to leave a radical on the bottom, so I simplified. Put that up there. Okay, so now tangent of, let's say this is 45 degrees, um, or, I'm switching back between degrees and radians. So 45 would be pi over 4. So tangent of pi over 4. Um, and I'm okay with going back and forth as I'm teaching this lesson because you should be able to go back and forth easily as well. And so I'm trying to reinforce that here. So tangent of pi over 4, tangent of 45 degrees would be root 2 over 2. That's the sine value. And root 2 over 2. You notice that's the same, so it's 1. Well, that makes sense. If we have 45 degrees, what's the slope of this line? 1. Tangent of 30, or, pi over 6, that was less than 1. This is 1. This is going to be more than 1. And then what's going to happen as we get really close, right? As theta approaches pi over 2, right? So theta is approaching pi over 2. Well, what's going to happen is that the x coordinate, right, cosine of theta, is going to approach 0, which means that if you have sine over cosine, this is going to approach infinity because we have the denominator in this function is getting really small. And that means the overall value is going to get really big. And then when theta equals pi over 2, so theta equals pi over 2, then cosine of theta is 0. So that means tangent of pi over 2 is undefined. Actually, there's a place for that right here, right? So the slope of a vertical line is, we'll go back to blue, undefined. What that means is that when we're graphing the value, or graphing the function of cosine at the value pi over 2, right? So if we have a graph here, and this is tangent, when we reach pi over 2, we're going to have an asymptote like that. Now we started at 0, and the numbers got bigger. So it would go up like that. Now let's take a look at the second quadrant. The second quadrant represents for us the angles pi over 2 to pi. And so we're going to be filling this in here. Right? So if this is pi, well, notice that when we first start, right? So again, like coming from this side, uh, we have a vertical line. So again, that's an asymptote. And then even if it's just slightly not vertical, just slightly over to the left, right? Just a tiny, tiny bit more than pi over 2, we're going to have a really big value because again, we have a tiny, tiny cosine value, right? So if sine of theta over cosine of theta, if this is tiny, not Timmy, tiny, maybe Tiny Timmy, some literature class though, Charles Dickens, different lesson. So if cosine of theta is tiny, then uh, tangent of theta is going to be huge, except that it's going to be negative. So the absolute value, right, the magnitude is going to be very big, but it will be negative. Why will it be negative? Well, because cosine is negative. We're in the second quadrant. Cosine has a negative value, and so it's approaching infinity, but on the negative side. And then, by the time we get to here, m, the slope is -1, so that's the tangent. Tangent value is -1. And then, right, and so it just keeps decreasing. So it goes from infinity to -1, and then down. We're going to use this as a marker, by the way. The pi over 4, 3 pi over 4, right, the 45-degree marks. That's what we're going to use to kind of figure out whether or not there's been um, dilation vertically. We'll look at those pi over 4 values and see, is it at 1 or is it at something else to see that dilation. But then by the time we get down to pi, right, again, we've got 0 because sine of theta equals 0. So tangent of theta equals 0. So if I'm filling this in, and by the time I get to pi, we'll be back like that, right? So big, big negative value, large magnitude negative value, going to 0. Okay, so now let's move on. We're going to see the same kind of pattern here. So going from 0 to here, this is a value of 1, so tangent of theta is 1, and increasing, right? So it's from 0 to 1, and then here, again, we have an asymptote because cosine, I'm going to zoom in, cosine of theta equals 0. So again, tangent of theta is undefined. But notice here that it's a positive value. Sine over cosine, both are negative in the third quadrant. So we have positive values for tangent going from 0 up through 1, and then through now to another asymptote at 3 pi over 2. So if I go back to this that I'm kind of filling in, at 3 pi over 2, I'm going to have another asymptote. It'll look like that. Now that looks the same as this, doesn't it? What I have from 0 to pi over 2 looks the same as pi to 3 pi over 2. And so that's the pattern that we're going to see. And then when we fill in the fourth quadrant, oh no, we're not going to do it in the fourth quadrant. But so this is the pattern that repeats itself here. Okay, now notice here that the period, in physics, I would call this T for the period. The period is pi, not pi over 2. It just repeats itself. And so we can go down to this graph now. So when we graph the tangent function, this means we will see vertical asymptotes, right? So I've already mentioned that, but now we make it official because we write it on the worksheet. It's not how you spell that, asymptotes. You see vertical asymptotes, and again here, oh, that's a note from a class I mentioned. By the way, e to the I pi plus 1 equals 0. That's true. It's the big 5 equation, sometimes called Euler's equation. It is beautiful. You can look into it on your own time. Apologize for the distraction. Now, again, the period here you'll notice from negative pi over 2 to pi over 2 is pi. And so when we're looking at this type of graph and we're looking to see is there horizontal dilation, we're looking to see has there been is the period pi or is it something else? Is it pi over 2? Is it 2 pi? Whatever it might be. Okay, so here's some of the features, right? Okay, yeah, like I mentioned. So again, just like the sinusoidal functions, there can be these transformations that take place, vertical, horizontal translations. You've got dilation, translation, etc., which are all dictated by um, A, B, C, and D as they appear in this form, right? And so the vertical dilation is A. You can think of A as the magnitude, kind of, right? Except that or sorry, think of it as the amplitude, except it's not really the amplitude because it's not only going that high. But when we have tangent of pi over 4, we know that should equal 1. So we're going to use that as our key to understanding whether or not there's been vertical dilation. The period should be pi, but it'll be given by pi over b, uh, based on whatever the function is. The phase shift with C, and then D is where the midline falls, where it goes up and down. And we know where the midline should be. The midline should appear when uh, theta equals 0 and pi and 2 pi, etc. Right? All the multiples of pi in the standard tangent function. Right? In these functions, it'll depend on what the period is based on pi over b. Okay, and so now let's take a look at some examples. There is here's an example of a function, and we want to know what are the values of A, B, and D. They didn't include C because there's no phase shift here. It hasn't been shifted. Notice that we have it passes through the coordinate 0, 0, it passes through the origin. So there hasn't been any kind of a phase shift. However, we do notice that the period here is pi over 2. Okay, and so we know that the normal period is just B. So I'm starting with this, that B times pi over 2 should equal pi, right? And so what does B have to equal? B has to equal 2, okay? So when I'm writing out this function here, I know that B is going to equal 2. Now, has there been any vertical translation for this? No, right? It's passing through 0, 0. Then, if I were to plug in one of the values like pi, for example, right? Because I know that tangent of pi, uh, but here it would be pi over 2, then, that passes through 0. And so D equals 0. And now I need to find out what A is. And so how am I going to find A? Well, again, I know that at the kind of what we call the halfway points, so between here and here, right? So on a normal function, the original tangent graph, that this middle would be pi over 4. Here it's cut in half because the whole period's been cut in half, right? The whole thing's been shrunk horizontally. But I notice that this is lined up with 1, and that's where I want it to be. That's what I'm kind of using as my quotes amplitude. Not really amplitude, but that's what I'm using as my measure for whether or not there's been vertical dilation. And there's no dilation here. And so um, in this case, A is just 1, right? We don't make it 0. The whole function would be 0. But in this case, A equals 1. So to write out this function, this looks like f of x equals tangent of 2x, and that's it, right? Because D is 0 and A is 1. Okay. Example 2. Okay, so I know that the period should normally be pi, right? And so I know that 2x, when is 2x going to equal pi? Well, it's going to be when x equals pi over 2. Okay, and so the period is pi over 2 because I know that value will give me the value I would normally have after just pi. So I'm using the standard tangent graph as my measure. For example 3, we've got a function where there is a vertical dilation, a midline shift, and we can see that there's a b value of 1 over 3, which is making a horizontal dilation. The question that they're asking, though, specifically is simply, what are the vertical asymptotes of G? Well, we're going to find the first vertical asymptote. We know that there should be a vertical asymptote on the original tangent graph, the standard tangent graph, at pi over 2. So I'm going to set x over 3 equal to pi over 2. All right. So it's, again, when this thing in the tangent function, when this thing equals pi over 2, that's when I know there's a vertical asymptote. Okay, so that's why I'm setting up this way. So x equals 3 pi over 2. That only gives me, though, the value of the first, the horizontal coordinate of the first asymptote. That narrows it down here. I already know the answer is C. But then they also have this, plus 3 pi k, where k is a constant. What's that about? Well, the thing is, here the period, right? So x over 3 equals pi. So I'm doing this to find the period. X equals 3 pi. So every multiple of 3 pi is another period and puts me back at that same place in the cycle, which is the asymptote. And so 3k plus 2, 3k over 2 plus 3 pi would put me at the next asymptote. And then plus 6 pi, right? So k equals 2. 6 pi would give me at the next asymptote, et cetera. So this is a general expression for all the locations of all of the or all the x coordinates for all the asymptotes, all the vertical asymptotes. In example 4, they give us a graph, and we've got to come up with an expression. Again, in AP Precalculus, this is one of the big themes, right? Going from expressions, from functions to graphs to descriptions to tables of values, all those different things, right? Being able to model it different ways, different representations. Um, And so this is what we practice a lot. So here we look, and this one actually has a period of 2 pi. We notice it goes from negative pi all the way to pi. So that's a period of 2 pi. And so what I have here is that b times 2 pi, because that's the period I have here, should equal pi. Right? I'm going to be multiplying 2 pi by something to make it equal to pi, to make it equal to what the standard tangent period is. And so b has to equal 1/2. And so that narrows it down here to a and b for me. But here's the other thing, is that I can tell there's a midline shift. This whole thing has been shifted down by a factor of -2. That's the new midline. That's where it's crossing in here. And so that's how I know that. It's halfway between, right? That's where it crosses halfway between the asymptotes. So I also have a downward shift, a downward translation of -2. And so the answer here is A. Example 5, we're just filling this in, finding the values of the expression using the tangent circle. Okay, so tangent of pi over 6, in my mind, what I would do is I would find the sine and the cosine and then put them one over the other and go that way. And then you'll start to see the pattern, how it works, right? Because the sine and the cosine for all the values that are not, 0, pi over 2, pi, they're all over 2. And so it ends up just being like the numerators, the sine numerator over the cosine numerator, etc. But anyway, let's get into it. So tangent of pi over 6 is going to be, so sine of pi over 6. So in my head, I'm picturing the unit circle, and I'm going from the 0, so from your perspective, right, the 0 up, and it's only, it's the smallest angle. It's like 30 degrees. And so it has a small vertical coordinate, so that's 1/2, and the larger horizontal coordinate, so that's √3 over 2. And so this ends up being 1 over √3, but we don't like to express it that way, so we do √3 over 3. Okay, tangent of pi over 4, that's the 45 degrees, and that's √2 over 2 over √2 over 2, and that's equal to 1. Right, tangent of pi over 3, that would be the quotes, what we call 60 degrees, right? And so that's a bigger sine coordinate, a bigger vertical coordinate, √3 over 2 over, and now this is just 1/2. The x-coordinate is the smaller x-coordinate, 1/2. This just simplifies to root 3. Notice this value now is bigger than 1, which is what we expect, right? If we look at the tangent graph, starts here and it's going up. All right, tangent of 5 pi over 6. So where is this on the unit circle, right? Well, if it was 6 pi over 6, that would be pi. That would be the 180 degrees. So this is 180 minus 30 degrees, just 180 minus pi over 6. Get it that way, or pi minus pi over 6. Really mixing the degrees and the radians here, but that's how it's worked for me to be able to think about it over the years. I encourage you to, really work on that ability to go back and forth between them. So anyway, that has a positive sign, small sign coordinate. So positive, I almost wrote a negative, positive 1/2, and negative root 3 over 2. Okay, and so this is going to be negative root 3 over 3. Okay, tangent 4 pi over 3. Now, where does that put me? Right, so that is past pi, so I'm bigger than pi. I'm down in the third quadrant, and this is kind of like it's pi over 3 from pi. I've gone to pi, and I've gone a third of the way around the bottom half of the circle. So I'm at the, what you could say, 60 degrees from the negative x-axis. Right, so I've gone all the way to pi to 180 degrees, and then I've gone another 60 degrees. And so that's going to have a large negative y coordinate, negative 3 over 2, and then negative 1/2, the small negative x coordinate, right? Both are negative because I'm in the third quadrant. And so this ends up just being positive root 3. 7 pi over 4. So I'm in the fourth quadrant at the quotes, kind of the 45-degree mark there. So I have a negative y coordinate and a positive x coordinate. So sine over cosine. And this ends up just being negative root 2. Sometimes I put the boxes around, sometimes I don't. Okay, tangent of root 3 over 2. Well, that's the 270 degrees, right? That's straight down. And we've already discussed that because we know that at that point, there is, it's a vertical line and the slope is the tangent and the slope is undefined. So this is undefined. Tangent of pi, it's all the way over on the left, 180 degrees. And I have sine is 0. And so this ends up just being 0. And then pi over 2, again, the vertical line in the between the first and the second quadrants. And so this one is also, I shouldn't write equals, undefined. Okay, so that's an introduction to tangent functions, the tangent graph, and tangent values, which we derive from the unit circle. Thanks for watching. Don't forget to like and subscribe.